Right, we are recording.
All right. Well, thank you, everybody. Thanks to Jay for inviting me to kind of give this talk. So what I want to talk about today is Hindley-Milner and you, and in particular, type inference. A short primer. My intention is not to get deep into technical details, but to give kind of an intuitive understanding of how type inference works. Show what an implementation looks like for basic algorithm W, and then in some sense the motivation for this talk came from application outside of just compiler design that could be solved by doing type inference. So my interest in this came from thinking, hey, if I could actually have my own version of type inference, not something that lived in the GHC compiler, that I could deploy in an application, I could solve kind of an interesting problem, or solve a problem in an interesting way at the very least. So here's the outline. I want to start out essentially with just a bit of history. Obviously, the Hindley-Milner, there's history to the people who have done the academic research that went into this. Talk a little bit about that, talk about type inference, in particular, like how the algorithm works, and then talk about applications. So if you actually want to use type inference to do something interesting, good or evil. Okay, so if you look at the 1978 paper by Milner where he introduces algorithm W, he has the following problem, which I think we can all relate to, which is how do you combine the flexibility of Lisp with the type discipline of Algol 68? So maybe a little bit more modern version of that is he walks through a couple of observations that as functional programmers I think we can appreciate. One is the observation that people talk about a lot, that static types are really nice because they catch errors. He mentions, writing Lisp programs and taking the cutter of an int and, the thing blowing up and him just being like, I wish the compiler was smarter. And the second observation is that putting type definitions, sort of forcing that type discipline, can be tedious. And at the time, what he was sort of interested in was a couple of things. One was a nice way to do polymorphism. So he wanted to be able to define certain functions, like a map function, where it's just a list of A's, for instance, and a map over this list of A's from an A to a B, where he wants that to be polymorphic. But where you're deploying it in a particular call site, you can say this is a map where those A's become ints or become strings or whatever it happens to be. So, he mentions that the way that you have to do this right now, I guess in Algol 68, for instance, is you essentially need to have a map for ints and bools and everything. He also mentions, and it was amusing to me, when I kind of thought about why type inference is really nice, it was kind of the second point, the idea of I don't have to put type annotations all over my code. And as a developer, that's really nice because I'm lazy and I don't like typing a lot of characters. He actually kind of sweeps that under the rug and says, well, it's true you don't actually have to type your method definitions, but maybe you want to do that anyway. So it was amusing that the main thing that most programmers now talk about in terms of improving their quality of life, he didn't really think it was a big thing. And finally, there was before a formal way to verify that a program was well typed, which in some sense is what algorithm W is about, that's what the W is supposed to indicate. There was concern that you wouldn't necessarily have guarantees that the type lined up, and to provide those guarantees, the thought was you're going to have to carry around type information in the runtime system, and that was sort of inefficient. So, in some sense, the type inference was as much about verifying sort of well-typedness in the compiler. So for us, I think the way we'd probably pose Milner's problem today is how do you get polymorphism? How do you write functions that are polymorphic without all of the overhead, right? Without having to either add explicit annotations or write functions that deal with all the different types that you want. Okay, so before I kind of jump into what the algorithm looks like, I wanted to give an example just so we're all on the same page for what does type inference really mean in a concrete example. So this is actually the example that he puts forward. This is in Haskell. He does the example in ML, which is the first language that implemented this, for map. So map is exactly what you'd expect. It takes a function, it takes a list. If that list is empty, then you just return the empty list. Otherwise, you apply the function to the head and then just recurse down. So if you look at this from just an expression perspective, where these are just identifiers, right? Where f and x and null and empty lists and all these things you just think of as just symbols, just formal symbols. Then there are symbols that are free, meaning they don't sort of show up in any definitional sense in the expression, but that are important. And these are things that sort of from outside the context of this function definition, your program would know about. So if you had other polymorphic functions defined somewhere, then you could talk about the types of those. We're going to call those free variables, and just to kind of enumerate the ones for this particular example, you've got null, which is a function that takes a list of somethings to a bool. You've got the empty list, which is just a list of somethings. It has that type. You have a type of head, tail, etc., and cons. So all these things are sort of pieces that you would have outside of the definition of the expression. That's sort of part of your type environment. In addition, there are bound values, right? There is f, there is x, there is map itself. So what is sort of important to understand what's going on is that you could write down expressions for essentially the types of these in terms of either unknown types or in terms of the other types that are in the system, right? So map you can write in terms of the type of f. F you can write in terms of, it's just a P2 to P4, but that P4 or that P2 also shows up in head. And if you look at this from just a puzzle solving perspective, and you weren't designing an automated algorithm for it, you're just a person trying to figure out what the types are, you can imagine doing reasoning where you looked at this with a set of constrained equations, where I'm just trying to figure out what the unknowns are. And in some sense, that's really all type inference is about, is taking a structured approach to writing down what you don't know about the types, and then solving a series of equations in a systematized way so that you can figure out the types of your unknown variables. Okay, so that's very kind of high level. The goal I was interested in initially when I started kind of reading about type inference was actually to write a algorithm W, something that did type inference for a particular application. So we're not going to go into GHC source code and look at how GHC type inference works. This is going to be a simplified example. We're going to show how to represent this in Haskell code. So there's sort of two types of structures that we need to be able to represent. One is the terms, right, our actual expression. And this is essentially just an abstract syntax tree where we've got a couple of different pieces. Our expression can either just be a variable, which just has some name. It can be an application, which just means I'm going to take some expression and I'm going to apply some other expression to it. It can be a lambda, where I have some named variable that goes into an expression. I have a literal, which can just be, in a simple example, an int, a bool, a string. You can have lets, ifs as other kind of constructs in the language, and fix, which handles kind of recursive calls, recursive expressions. So for this talk, I'm going to concentrate mainly on what's in the green. There's obviously a lot of interesting nuance to things like fix, but for this talk, we're not going to kind of get into those details, because I think you can get an intuition for how the algorithm works without some of the kind of distracting nuance from that. So in addition to the expressions, we also need a way in the code to be able to represent the types. And the types are themselves kind of have a tree structure to them, where your type can either be something that's variable, where you're just going to represent that by a t-var. It can be a kind of constructor type, where it's a type of one of the kind of primitives in your system. Or it can be a type of a function, which is just, you take in a particular type and you spit out a type. And of course, you can do this recursively, so you could get function, multi-parameter functions through kind of your typical currying. And also lists of things which you can handle. Okay, so I didn't want to, if you read some of the literature on this, I think it has a tendency to be a little bit intimidating because it uses the kind of formalism of mathematical logic. And if you don't have that background and you look at it, it seems a little bit overwhelming. It is, I think, important to provide something to kind of understand what's going on. And for me, what was useful in kind of making sense of this was to actually see graphically what's happening in the syntax tree and how the algorithm is essentially walking up and down that tree. So the example that I'm going to walk through is something extremely simple. So this is just a lambda expression and what the AST looks like graphically. So the function takes in an x, it adds 2 to that x, and then makes it essentially a singleton list. So if you were looking at this problem and you were thinking, like at the beginning, what information do I know, right? What information, if I were trying to do type inference, and in particular what I'm trying to do is I'm trying to figure out the type of this expression. What is that expression? Then the leaves of this, I sort of know something about all the leaves. I've imported from the outside what, this is sort of free in this expression, what the cons operator is, which is essentially it takes some A and takes a list of A's and spits out a list of A's. My plus, in this case, and for a kind of simplified language, it just deals with integers. So plus takes an int and spits out an int to an int. X, at this point, I don't know anything about x until I do some inference. So it's just some variable with some type that I don't know, an A1. My literal 2, I do know something about that. That's just an integer. And then my empty list, I also don't know very much about. So this is, in some sense, kind of like initial data for solving this constraint problem. So what else do we know? If you were going about reasoning about how to do type inference, just as a person trying to solve a puzzle, you would go through looking at your application, your lambdas, and you'd be able to make assertions about what the types of the sub-expressions, how they have to relate to each other. So a literal, that's actually pretty straightforward. If I were to say, an L int with an int, what is the type of that? Well, it's essentially an int. So I'm using the double colon in kind of a Haskell sense to indicate the type. I'm putting the type as represented by our type construction from the previous slides. Boolean is as well, the literal bool also has type bool. Application, what can I say about that? Well, I can say that the first thing that I'm passing to my application, the first expression has to be a function. I've got to apply something, I have to apply it to a function, and it starts in some type, I don't know what it is, goes out to some other type, I don't necessarily know what that is. I know that the second parameter that I pass in here has to be the same type as what the input to that function is if it's well typed. And I have to know, and I can say that the type of the overall application is essentially T2. In the same way, a lambda expression, I can say that if my E1 is a type, then my lambda expression essentially goes from some other type, whatever x ends up being, to T1. In the variable x, I don't know what the type is, but I'm going to grab that from my environment. So this is going to be, it might just be some unknown type, but depending on what information, when I actually need to do an inference on that, I may be able to infer what x is in particular. So sort of representing that as lookup. And you'll figure out, I'll talk more about what this means in a couple slides. But this is, if you were just sort of approaching type inference from a problem that you wanted to solve with pen and paper, these would be kind of assertions that you would make, kind of laws that you'd like to be able to use to do the inference. So of course, we don't want to do this in a just kind of like ad hoc, way, we need some way to think formally about what it means to assert things about types. So the term unification is used to talk about what it means formally to say that two types are kind of the same. And essentially what happens, what it means under the hood is that you have a substitution. So to say that you have two types is, for instance, that I have some type variable A2 and that it's kind of the same as something that's a bool to some other type A3 means that I have some map from the type variables, a map that goes from the type variables to some other types, and I can apply that map to the expression on the left and expression on the right and get equivalent expressions. So that's what unification means. That's what it means to sort of assert two types. That I have a map that goes from type variable to type, and they don't have to go all the way down to whatever the kind of concrete types are at the end. But when I've unified two things, I need to be able to say that I've got a substitution I can apply to both expressions. I sort of apply it recursively. That gives me the same kind of expression. So in this case, if you were to actually look at what is the substitution that you would do, it's pretty simple in this case because your expression on the left literally is just a type variable. So what do I say? Well, I just take A2 and I map it to whatever is on the right-hand side. Okay, so if we were to take this idea with our example and think about sort of unifying from the bottom up, applying, if we just look at the very first node, first app node from this plus and x at the bottom, then basically we can reason in a way that says our app of fx needs to be a t2. The f that kind of comes into it is some t1 to t2. The x that goes into it is just some t1. And unifying the expressions, I can verify that this longer expression, which is int to int to int, has this t1 is the same as that guy. So I would say that there's a substitution that goes from that a1 just to a type of int, and that my t2 is essentially what's the second part of that arrow.
How do you interpret that? Like, do you read that up or down, or what's that over on the left? T1, T2, T2 up?
Yeah, sorry. So this is the line, you mean?
Yeah, the lines and all.
The line is supposed to essentially be brackets around the entire expression.
Okay, but how do you read it? Do you read it up or do you read it down? Like, how do you turn that into English, what that says right there?
The T1 to T2, or
the whole thing. Like, what's the order? Like, when you look at that, I don't even know where. Like, do you start at the top and go down? Do you start at the bottom and go up?
So the red is a representation of the type of this box. Using if you were doing this in Haskell, you would just say int, arrow, int, arrow, int. That would be the type. Now, I'm sort of writing the types in terms of the constructor, the type constructor that we defined. So the type, the way I represent types in my in our kind of type construction is tcon int. That's how I represent int. And the way I represent an arrow is with the constructor of tarrow. So this is a little bit of extra. It's a lot of extra syntax around what you would do in Haskell, but it sort of shows you code-wise what are the representation of the type of this bottom leaf is going to be in our system, and then what the type of that var x is going to be, and after we've done a unification step, what the type of this guy is going to be, which is sort of tcon int, tcon int. Does that answer your question?
We can
maybe. Okay.
Because I think my question is literally, how do you read the logic of the bars? You've got the little bars, and
they're just labels, right?
Let's go back. Imagine that if I was using a different program to do the graphics, I would have done curly brace around that section.
Okay.
Does that
Okay, so it's literally labeling. I thought that was like a logic representation.
Nope.
Oh, I thought logic representations kind of look like that.
They do. Yeah.
Got it.
Yeah.
Okay, that's
so I apologize for that confusion. It's not.
Okay. Okay, yeah.
Yeah, I've actually explicitly avoided the syntax of mathematical logic here. But,
Yeah, but it looks
just like
can't avoid it, right?
That's a good piece of information. I should probably make that curly.
Yeah, curly brackets would help.
Yeah,
I think, or curly lines.
Okay, so if you were to actually write in code what unification is, this is actually, I'll give you the reference at the end, but it bears kind of mentioning here. There's a really great online resource called Write You Haskell, which has basically walks through creating a compiler for Haskell from like just basic principles. It's not totally complete, but it has a really great description of Hindley-Milner, along with in Haskell how you would reference something, and this code is largely lifted from that. So there's a little bit of kind of code background here that I'm going to wave my hands at. We're running in a monad, the infer monad, which is essentially something that lets us carry around state and throw exceptions. So that's essentially what we're doing. The types are the types that we talked about previously. There were a couple of slides away. And essentially our unification is trying to output that substitution, right? So that literally is a Haskell map from a type variable to a type. So that's what we're trying, when we do unification, we take two types and I'm trying to get that substitution map. So that's what this unify function does. So a way to sort of, encode the rules about, our assertions about what happens when you are kind of unifying two types, we're literally doing by just casing out the different situations. So if you run into an arrow, where you're basically trying to unify two arrows that have an L and an R, basically a type L that goes to a type R, and a type L prime that goes to a type R prime. How to unify those? You actually do it in exactly the way that you would assume, sort of recursively. I need to assert, I unify and figure out a substitution map for making L and L prime be the same. So I get that S1 as that first substitution map. I then use that substitution map on my R and R prime, and then recursively go through to unify those things. So now I've got, basically something that I've learned about what the type variables are from L1 and L prime. I've got S2, which tells me about what I've learned from the type, from unifying those things for other type variables. I need to compose those two maps because there may have been type variables in S2 that after I've done some unification I've learned about that are in S1, so you can compose those two maps. For the type variables, if I'm basically unifying a type variable with anything else, then it's really straightforward. So remember from a couple of slides ago, I said if you had type variable like A3 and then some complicated expression, how do I do a substitution of that? Surprise, it's just take that type variable on one and sort of map it to the other. That's all that binding does. It doesn't matter which order it is. It sort of works whether that type variable is in the first or the second position. The type constructors are more restrictive. Basically, these are primitive types. And if I'm unifying those two, I'm not going to learn anything new. There's no type variable substitution to be learned. The only thing that could happen is that I screwed up and basically did something wrong. So if you're doing unification of two primitive type constructors, if they're the same, you're good. If you somehow have derived at this point that they are different, then you've screwed up somewhere.
And when you say you mean the programmer who sort of wrote the program?
Yes.
Okay.
Yeah.
Well, what's the null subset?
It's just null substitution. It's just basically
they're the same.
just empty.
Got it. Okay.
The and then lists again you go recursively, and then anything else. So if you found yourself in a situation where you had a list and an arrow, that's no good, right? You've done something wrong. I mean, in the same way that if you tried to unify an int in a car, you'd have a problem. So this is, I mean, in some sense, this really is just a encoding of, what our assertions were for this. And there's similar, kind of code and unification around lets and ifs and the fixes as well. Okay. So it's not just a bottom-up algorithm. That is where kind of the interesting things are happening, the unification steps are happening. But there's also kind of context that needs to be passed down from the top. So when we talked about the what's happening at the leaves, we said this var x leaf at the bottom had some particular type, and I don't really know what it is. I said, you look it up from the environment. The way to represent, what you know about that type environment is this type end, which is essentially a map for all the different variables in your system to a scheme. Now, a scheme is essentially a way to talk about types that have existential quantifiers for for handling polymorphism. So there's some nuance to how these pieces work. I think from a high level, the important piece is just as you're walking down the tree, sort of essentially doing a depth first search on your expression, you're going to encounter situations where either you hit a variable, in which you need to look it up in the environment, or you hit a lambda. And the lambda says, I've now defined a new variable in my system that might end up showing up in the expression that's going to be somewhere down the tree. So as I'm walking down the tree, I'm growing my type environment, and then potentially using that to look up variables when I get from the bottom. Okay. So if you combine what's happening from basically going to top down, defining the context, and then pulling everything back up via unification, that is essentially what Hindley-Milner inference is doing, and what algorithm W in particular does. So if you kind of look at how this works, it's essentially a depth first search algorithm across where I'm passing my type environment in, and I'm marching across my expression and passing up the substitution and the type. So I kind of start here. Oh, I can't actually.
Yeah, I noticed there was something weird about the pointer there. So yeah, you might.
It's one. Right. So you basically start out your lambda. You introduce a new type variable for this x that updates your environment, as I said, and then you say, okay, I'm going to infer whatever is in this expression, so just call recursively the e that's inside my lambda, where I pass this environment, get back my substitution and my type, and then what's the type that I pass back up? Well, I just pass the same substitution, and then I apply that substitution to my lambda expression, which is the new type variable that spits out t1, which is the type of the expression that I sent. And the same thing, like all the way down, if I hit an app, I'm going to have a new type variable that is the type of my app. That's what I'm going to be passing back up. And I recursively go down, get the substitution for the expression on the left and the expression on the right. Unifying those things to get the S3, pass the S3 back up, along with my new type variable. And the literals are pretty straightforward. Those are always going to be leaf nodes. There's no recursion back down there.
So that's top down. Where's the bottom up?
The bottom up is my return.
Oh.
Right. So I'm kind of calling myself recursive. There's recursion, right, which kind of goes. The unification happens with on the bottom up. So I'm kind of grabbing my. In this case, I'm grabbing my S1, my T1, my S2, my T2 from below, and then unifying those things and passing my substitution back up.
Okay. What's fresh?
So fresh essentially just grabs a new type variable. So you have like an infinite list that lets you just get distinct characters. So the way in the code, the way it's implemented is you just have an infinite list of strings that kind of get generated, and you just grab the next one off the list. So you get A1, A2,
a new variable,
A4, A5.
Got it.
And so that's the state in the infer monad?
Yes.
Okay.
Yep. Yeah, so it literally, it's just a get. You hit the tail, whatever your list is, go back. Okay, so I want to spend some time talking about the to me, I guess, what's sort of interesting about type inference is, not just what's cool about GHC or other kind of programming languages, but this idea of type inference as something that has utility for an application. So, when I first started thinking about type inference, what I always appreciated about it was that it allowed me to be a little bit lazy. I can write code, and instead of having to put in, pieces of information, things that the computer should be able to just figure out from context, it can figure out. So I started thinking about that as just a concept, right? If you're a user of a program and there's information that you don't want to have to input because it's a pain to do, wouldn't it be cool if you could have the computer figure out what that is from context? So one of the specific examples that I was thinking through came from kind of a boring problem, but it's one that kind of working in the law firm we encounter a lot. So we do a lot of kind of document generation, and in general, the document generation is either on the side of relative complexity, where very complicated documents that have a lot of logic for how they get put together, or that needs to be completely automated. So people have a template, but there's nobody doing data entry to fill it in the templates. But it turned out that there was enough of a need for this kind of middle category that we thought, all right, we're going to extend this platform that we have for doing document generation so that we can do, if people need to be able to just do a little data entry and it fills in the blank with a date or a name across 30 documents, that saves some people time. And we have internally a kind of syntax for being able to create forms for Word documents in Excel and other sorts of things that has a particular syntax. And the syntax is set up, you can kind of see here, but it's more or less self-explanatory. You have a client, right, which is just going to grab some client piece of information, and then you're going to try to get the first name for it, and that's going to print out to the screen, or that's going to fill in with that blank. You may also have a date, and this is just sort of Unix formatting for that particular date. This is sort of a joke contract where you're negotiating terms, and either they're favorable, in which case whoever you're negotiating with owes you a lot of money, or they're not favorable, in which case you owe them a lot of money. But this is sort of a Boolean thing, right? Whether it's favorable or not. And again, the attorneys with first name and last name are just sort of text inputs. So when we were thinking about building a kind of data entry interface to this, where if you have a whole bunch of documents where you've kind of templated them this way and you want people to be able to fill in the blank, there is a type difference between the kinds of information you're putting in. A first name is a text, a date is a day, a favorable is sort of a Boolean value that's true or false. And if I were making a user interface for that, I'd really want the text to be a text field, I want the date to be a calendar picker, I want the Boolean to be a checkbox or something that kind of does that. But I really didn't like the idea of either having the users have to go in and either have extra widgets or extra kind of information to put in to say, here's a date, oh, by the way, this date is a date, and make that a date widget, right? I mean, you could try to do some naming convention thing, but if you want people to sort of make their own templates, with some kind of limited syntax, then someone's going to pick the wrong thing and be confused. So, the alternative would be for every single template, to write some code where you say, oh, in this case, I'm going to do a whole bunch of web programming, really just painful, uninteresting web programming. So it kind of occurred to us as we were thinking about this that it really feels like a type inference problem, right? I kind of know that first name, it's a function, it takes in something, it spits out a text. A client takes in nothing and spits out, who knows, a person in this case, right? A date spits out a date and then gets formatted in a particular way. So I know that this thing, what's the type of this guy? Well, it's literally something that takes in a date type and spits out text. So I should be able to back out from that date is a date. In the same way, this is sort of our kind of like Boolean or our kind of ternary operator. I should be able to back out the fact that favorable is a Boolean. And attorney first name, attorney last name. I should be able to back out the fact that attorney is in some sense a record type that has a first name and a last name associated to it. So the long and short of it is that having even just a very rudimentary type inference algorithm has allowed us to sort of do all that stuff programmatically. So this is the kind of example of what we have rolling right now, where we read through the document, and I guess I'll show you the specific steps, but after this talk, after what I've said before, it's probably pretty straightforward about how all the pieces fit together. But essentially, we can take a document, parse it, get all of the variables out, and figure out the types of them, and based on the types, be able to programmatically generate the web form with the right widgets. So first name is a text field, date is a date picker, favorable, in this case is Booleans, we just sort of represent with the checkbox. So, digging in a little bit more, the syntax that we have, there's certain information that we kind of load into the environment. One has to do with what our dot operator means, right, which is essentially like a function composition, but sort of going right instead of going left. The date formatting, which can occur in a couple of different ways, always has type date into a text. The question mark is our ternary operator, which lets us know that we're pointing to a Boolean. So the steps for sort of putting this together was essentially parse the document and get a lambda expression, find the free variables, basically the kind of keywords that are going to show up in there, form a new lambda expression so that those are all kind of things that we pass in, perform type inference to get the type of this new expression, and then we can essentially pick off the types for all the input parameters to figure out the types of rows. So,
is that a typo there with the two Y's in a row there? Step 3?
Yes, yeah,
Okay.
that is a typo.
And what's an LC expression?
That's a lambda function expression, which actually is also probably a typo. In the E prime, I don't necessarily need that in there. I guess the LC should probably have been over on this side. So is that clear? I guess sort of the.
Mm-hmm. And so basically, you're predefining that term dot term 2 is, so basically you're saying, hey, here's my basic structural components,
exactly.
And then you go there and figure out the types based on those minimal.
Exactly. Yeah. We should have a few different pieces.
Yeah.
And it'll figure out the fact that these are all. I mean, one thing that we're actually discussing whether this is good or bad. The fact that attorney, has a first name, an attorney has a last name, a client has a first name. We've inferred the fact, it's assuming we're not allowing for the terms to be polymorphic across where they're used in the expression. So it infers the fact that whatever client is spitting out and whatever attorney is spitting out are the same thing.
Oh.
So when we go back to create the record type for them, you'll see client, even though client last name doesn't show up anywhere, it's like, oh, it's spitting out the same thing. It's a record type. It has a first name and a last name. We've had some discussion about whether that's good or bad, in the sense that in some cases people may be filling in information that is more than what is needed for the form. But at least it lets you understand the structure in a way that's kind of semantically meaningful.
So you're saying that you automatically inferring that a client also has a last name?
Yes.
You are?
Yeah.
Got it.
And essentially the way that that's working is just inferring that client, all of our terms are essentially functions. So client takes in a unit and spits out a type. That type, and first name, takes in whatever that type is and spits out a text. Attorney, because it uses first name, has to also basically take in that same type. So let's say client, goes unit to A, and first name is A to text. Since I've unified that with other expressions, attorney, which also has to compose with first name, that means attorney spits out unit to A as well. So client and attorney both spit out the same kind of A. It means
That was a decision that literally you're like, yeah, that sounds good. Let's make it that way. You mean you could have said
I
no,
could have totally done
it.
Yep.
Yeah.
And we may go back and do something different. I mean, I guess the thought was in cases where you could imagine deriving widgets that work for some composite, and you'd like to be able to like reuse that whole widget, it might make sense to be able to connect those. But as I said, that's actually an active point of discussion for us, whether that's a good or bad thing.
And am I correct in understanding that all of these various types could be backed by whatever storage system you want? So eventually you could validate that the client whose first name is being put in is actually, they have a relationship with the attorney whose information is being put in down below as an additional check.
Sure, yeah. If you wanted to actually pull that information from somewhere else and say, all this is doing is just sort of telling you the types of the things. If you wanted to turn that into other kind of verifications, you could try that. So this kind of got me thinking about some other ideas in this space, which are, other places where people are doing, there's information and people don't necessarily want to spend the time to give you all of the specific information, but it feels like a machine should be able to figure it out from context. So, natural language is the kind of canonical case where, at least as humans, and for a lot of sophisticated computer NLP algorithms, they can kind of figure out what things mean from context. So I started thinking, does it make sense to use sort of types and type inference to be able to say something about that? And I mean, this is just sort of speculative on my part, but it's some things that we've been thinking and talking about internally. So you can imagine, two questions, right? What's between 10 a.m. and 12 p.m.? Well, between, which maybe is sort of a polymorphic thing, in this case is dealing with times. So like, what do you want the answer to, what's the type of the answer that you'd expect? Well, you expect to be a time. What's between Denver and Boulder? What's the type that you would expect to put out there? Well, you'd expect to put like a city. Right? So is there something kind of interesting you could do in kind of natural language processing or semantics to use sort of type inference to know what between means, not based on some big machine learning, although obviously that would be useful, but just on the context, right? The fact that 10 a.m. you're talking about a time, 12 p.m. you're talking about a time. Okay, the answer to this question needs to be a time. So with that, I guess we'll conclude with references. So if you're interested in this, I really encourage you to take a look at Milner's paper. It's super readable, and I guess it's kind of nice to go to the source. And then for kind of practical code, if you want to sort of do some rudimentary type inference at the application layer, there's different libraries, but this Write You Haskell actually does a really great job of one, giving you code that you could use, and also giving some sort of description about why it works the way it is. Thank you.
That was actually
Questions?
really good.
Yeah.
Thank you. So because the whole concept is, like, you gave this kind of really trivial example